All right. Good morning, good day, everyone. I'm sorry. All right. In this video, this is all about exponentials and their final lesson for the semester. I'm so excited. So let's get into it. All right. Let me browse through these announcements for those who was absent. So look, go ahead and complete your project by December 8th. Let's get it done. Let's move on. All right. Make a review week. It's going to start actually this week on December 3rd. It's going to keep going to December 12th, the following week. All right. I'm not something nothing else after December 8th in terms of homework and all of that. You do have lots of pair of things to do. You got to review and study to do for midterms. Um, I thought that we was going to do some intense work that last week, but I decided we ain't going to do that. No, I'm not going to do you like that because I need for you to process, review, and master things that we have spoken about throughout the school year so far. Reminders, complete your project. Yeah, do your little study guide when you have some downtime. I'm gonna make sure everyone have that downtime to do what they needs to do. And then do Savas online for the EBR benchmarks and wherever else you are missing. All right, I do have an optional assignment for you. That's gonna count as a replacement grade, so replacing something terrible. All right, so I told you that the science portion of the ACT it does tie into mathematics as well as certain statistical components to deal with. So I want you to focus on that. All right. I know me and Miss Antoine we do work together, and some of my stuff that we do talk about do overlap to a certain degree. I know in terms of algebra 2 it's mainly the graphs and it's, laws of exponents and those things. And of course dealing with those decimals. All right, so the science ACT, there's 20 questions. I mean, to get a score of 20, 17 questions must be correct. 17. If there's time provided, see me so I could explain it in detail. However, this optional assignment for the ACT Science would not give you an exemption. It give you points, but not an exemption. Something good will happen out of it. I, as your teacher, make that decision what is going to happen for you. You don't get a say in it. All right, and we will talk more about the science ACT, but just please know that it's not going to be a thing that's going to move you to an A or a B or something like that. Because ultimately, I am a math teacher, so math is the priority. It's just science covers a portion of the math stuff that we do cover in Algebra 2. All right, let's go ahead and get to our lessons deal with exponentials. Now, for my B day, you've been taught this already, so you know to go to Desmos and do the work. All right, we got a lot of I can statements to deal with, but we're gonna cut it down. So I ain't gonna talk too much about the I can statements because we did talk about it, but I don't want you to spend too much time dealing with each part of it. However, when we go through and do these throughout the lesson, you should be able to meet the success criteria. So you should be able to explain the function and how it changes in the context of the problem. So the characteristics domain range horizontal asymptote, which is an exponential function only, not vertical. So that's going to be the y, not the x. All right. You're going to create and correct a model. So you're going to create a model to explain why it fits the situation that's given to you. Use your model to answer the question clearly in a full sentence because you do have to write and you have to explain what you are doing. So, For those who are taking my midterm, please note that you have to explain your work. All right, so let's go ahead and talk about features of exponentials and get it out the way. All right, so decaying factor, exponential decaying factor, exponential function, exponential growth function, and growth factor. That's the vocabulary for this section. All right, let's talk about the example one, key features of exponentials. So, what is your domain, range, intercept, and asymptotes, and end behavior of this function? But before you could do that, you must know what an exponential function is, which is a function in the form of f of x equals a times b to the power of x, where a and b are constants, where a cannot equal 0, b has to be greater than 0, and b also has to not equal 1. Right? So, all this is telling you is that when you're dealing with your exponents with an exponential function, like you're going to start with an integer, positive, like 3, times, let's do 4 if we want to, 4 to the power of x. So this is b right here. B cannot equal 0, it cannot equal 1, because if it does, this does not exist. You won't even get a graph. So that's the reason why the b being your base has to be greater than 0, but also not equal 1, has to be greater than 1. So that's why you never hear or see a function that looks like this, 1x to 1 to the power of x. That's not going to happen ever. All right? And again, with a could be any integer, but it just cannot equal 0 because anything times 0 makes it all 0. So if I was to say 0 times 1 to the power of x, that's just going to be 0. So we can't have that. So take this moment and go to the decimals and plug in this function. When you plug in this function, you have a graph like this. All right? So let's go answer the question. The domain is going to be always, forevermore, all real numbers. All right? Any exponential function will always, forevermore, will have a domain of all real numbers. Your range, your y values, y, has to be greater than 0. It cannot equal 0 because it doesn't touch us at 0. Because it get close to it, doesn't touch us at 0. And that is called your asymptote. And because it's an asymptote, it's a horizontal asymptote. Now, one thing that we got to be careful with your horizontal asymptote is dealing with the y, because if you draw your line, it's cutting through the y-axis. Horizontal cuts through the y-axis. Horizontal cuts through the y-axis. Because if I was to draw a horizontal line cutting through the y-axis, y gets close to 0, but it does not touch. This touches at 0, so therefore, my asymptote, y cannot equal 0. You could say that, or you could just say 0 if you want to. Because when you're saying y cannot equal 0, you're pretty much talking about like the range and stuff like that. So let me make that clear to you. All right, your end behavior. This is not something that's talked about too often, but I guess we could get through it. So from negative infinity, from x, y approaches to 0. So it's talking about the asymptote, could get close to, but there's not touch. However, as it goes to positive infinity, keep going, y keeps going too. So that's why how you deal with the end behavior. Again, the end behavior is just talking about what's going on with the direction of the graph. Again, from this side, it being negative infinity from some small number, but it gets close to, but it does not touch at 0 for the y. So that's why it's like x approaches negative as s approaches negative infinity, y approaches 0, but again it never touches because of the horizontal asymptote. And again, when x is positive infinity, y is positive infinity. So that's where that's come from. All right, good. All right. I know in class we have did the decimals, and we plugged this in, part B, and we realized that the only thing that really changes is your horizontal asymptote stays the same as your y-intercept. Your y-intercept becomes 5. Now, I know in class we did not talk about end behavior, but for the purpose of this lesson, we're going to talk about it here. Also on your homework. So, let's look at as x approaches negative infinity. Guess what happened to y? Y is still infinity. Because remember on this side, x is negative on the left hand side, but y is positive. So from negative, when x is negative, y is positive. All right. However, when it gets to the positive side, as x approaches positive infinity, it keep going, but y will never touch 0. So that's how you deal with the end behavior. And we're going to talk more about that in class if you need it. So when you're doing the homework today, you don't necessarily need to do end behavior because we could pick up and discuss that a little bit more next class period. All right. Pause the video and try this out on your own. I'm not going to tell you the answer because if you want to know the answer, come see me in class so we could discuss this. In addition to, I do want to make this clear, I do adore Savas. Savas has good videos to look at as well, besides myself. So make sure you look at those too. So I want you to try this on your own, and we're gonna keep it moving. If you was here, look at your notes. All right, transformations. You guys do a good job with transformations already. So what I want you guys to do for me is to talk about the transformation. So now, in the past, we just talked about which direction the graph move, up and down, left and right, stretch, compress, flip, or not. But now, we're going to have to talk about how the transformation, changes the characteristics, which is a question I asked you guys in the beginning, but I mean, you guys did not know how to break it down. So let's read this problem. Graphics function. Describe the graph in terms of the transformation of the parent function of f of x equals 3 to the power x. How do the asymptote and the intercept of the given function compare to the asymptote and intercept of the parent function? So we just comparing the original function to the transformation. And when we do that, this what happens. So your intercepts from the original to the transformation, y-intercept there stays the same. Your asymptote stays the same. The only difference is your end behavior and your range. So we know the blue of the range, y, is greater than 0. Can't equal to 0. The range cannot, because it becomes undefined because your horizontal asymptote is 0. And that's for the blue graph. For the red graph, your range becomes y is less than 0 because it get close to, but it cannot equal 0. So, because the horizontal asymptote of the red, which is the transformation, also equals 0. Alright? Now, again, I did not talk about the end behavior because I guess we could do it. So let's just do it for fun. Again, I know we didn't talk about it in class because I was trying to say that for another day, but if we need to, let's do it. So, from negative infinity, so we're dealing with x, x approaches negative infinity. As x approaches negative infinity, what happens? Well, y approaches 0 because it gets close to 0 but never touches 0. Alright? Now, and I'm doing the blue one for you. I'm dealing with the blue function right here. Okay, then on the right hand side, as x approaches positive infinity, guess what y does? Y also approaches positive infinity. Now, just to kind of put you on a cliffhanger, I want you to just look at red to kind of figure it out on your own in terms of the end behavior, so we could discuss that further. I have something to talk more about. All right, so far so good. And also, I do want to make clear, all this examples you see come directly from our textbook. So none of these are made up problems. All right, so dealing with the transformation, we want to talk about, as we did in example 1, comparing the original function 3x, f of x being 3 to the power of x, and we compare it to the transformation as x, h of x equals 3x to the power of negative 4. So when we put those two functions in decimals, this guy and this guy, we get this graph right here. And we realize the end behaviors of both of those are the same. The domain always stays the same. The range changes, asymptote changes, and your intercept has changed. Your intercept has changed. So that's all that is right there. So that means that this back of the function, which we know is k, remember the letters a, h, and k. We know that k really help us determine our horizontal asymptote. K determines a horizontal asymptote. K determines a horizontal asymptote. K determines a horizontal asymptote. So with this function, this is k being negative 4. Horizontal asymptote is negative 4. Y equals negative 4. And of course, we also know k tells us about our range. Again, k tells us about our range. So again, our range for this red function, which is the transformation, y is greater than negative 4. Alright, so far so good. Alright, I want you to try these problems. I want you to do both A and B. But just for a reminder about A, In decimals, if you try to put in 5 to the power x plus 3, what's going to happen? You're going to get 5x when you try to type it in plus 3, which that's not it. Now, many people so far today have found a way to get past that without any problems. So the easier way, if you want to do for exponential functions in decimals, do 5 raised to the exponent, open your parentheses and do x plus 3. And then close your parentheses. When you do that, that's an easier way about it. Or if you have any stuff that you worked on in decimals, you could repurpose what you wrote. Now, also there were some other students who figured out another way of doing this. So what they did is type in 5 and then the exponent. They start out with the operation plus 3, and then they move their cursor back and then put x in front of it. So you could get back to what you wrote right here. So I want you guys to try this on your own. I'm not going to say much because we've done it in class. Refer to your notes. All right, modeling exponentials. Exponentials, that's it's a applicable thing, y'all. It's very real. You know, this is something that people of a certain skill use in their day-to-day operation. And for those who deal with money. All right, so here's a situation given to us. The population of a large city was about $4.6 million in the year 2020 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over a 4-year period? So, anytime that they give you a specific number of years, you're going to use this model right here. This is the model you are going to use. All right? Because this is your exponential growth model. And when you do that, this is going to be A is going to represent your future. P is going to represent your current. R is your rate. T is your time. All right, so that's those pieces are already done. So let's take this and apply it to the situation we have. So to create the model, again, the future, or in this case, P, the population after the years. P, we use here, which this P right here, represent the current. So this is the current population in 2020, which is 4.6 million, so 4.6. Now, so we got the 1 plus the rate, 1.3. We gotta make Miss Antoine proud, y'all. So, how do we convert 1.3% as a decimal? Now, many of you guys have made her proud, and you have told me that you're going to write decimal point, move the decimal point in one place, replace it with a 0, 0.13, and that is correct. Now, and when you add 1 to that, 1 plus that decimal point, you get this right here. So that's the model that you created. And you explain to me why. Because this model deals with years. So again, you have to be sure to write and explain this in terms of years. So let's move on. So we created the model. Now we have to, if the population continues to grow at the same rate, what is the population in 2050? So then you guys in a little secret before we continue. You know this is how they predict the population in terms of every people by state and city when they're trying to project the population in terms of moving buildings, creating buildings, constructions, all of that. So that same model is also used in terms of construction when they're trying to build stuff. So according to Baton Rouge, we're supposed to have, I don't know the exact number, but we're supposed to have more people moving in. Moving to Baton Rouge. So that's why if you drive through Baton Rouge with your people, you see a bunch of apartments being thrown together, a bunch of houses being done because the exponential growth of the population of the anticipated population of Baton Rouge. All right, enough talk, getting back to it. So we know from 2020 to 2050, that's 30 years. Put this in decimals, and once you put this in decimals, you get your answer. Now, when it comes to modeling, do not forget, you just give me just 6.78, you have to write me a statement. Remember, a statement. If you cannot give me this statement, you cannot get it correct. And again, when you guys take my midterm, it is for explanation pieces only. All right, so I want you guys to take a moment, try this problem out. I'm not gonna say much about because I know on your homework you got this. Use what's being talked about. Well, actually, try this problem out, but I am going to move on and give you some additional support to helping you with that. So again, I'm just following through your textbook personally. I would have not, put this, problem in front of this. This is something that you need to know beforehand because there's certain language you need to know. All right, exponential growth and exponential decay functions quantifies the increase or decrease by a fixed percent during each time period. Given an initial amount A, and then the given rate increase or decrease, you got to find the amount of A or T at the T time periods given by these formulas right here. All right. So when you're dealing with the growth or decay factor is equal to B, and where the ratio between two wild variables is consecutive integers dealing with x. All right, so just reading this is just tell you about how the exponential decay model and growth model exist. So when we say growth, we talking about population, money in the savings account. When we talk about decay, we talking about buying something, like for example, a brand new car. So when you buy a brand new car, like 2026, is going to be worth a certain amount. But as the years progress, like say 2040, the car is not going to be worth a whole lot of money. Even your Rolls Royces or whatnot loses values over the year. All right. All right. So example for interpreting exponential functions. The y function 24 times 0.8 to the power x can be used to model the value of the car in thousands of dollars years after it purchased. Does this function represent exponential growth or decay? So remember, when you talk about car or a percentage, like or anything like that, well, not art, but a car for sure, the price is the worth of the car decreases. So it's going to be a decay. Also, if you look at B, you got 0.08 because it is less than 1 is a decay. So I gave you two details. The first one dealing with the situation because we're talking about, a car situation. And we know that a value of a car decrease in value over the years. And also your B is 0.8, so it decreases. Now, what is the rate of the decay for this function? So, we create ourselves a little equation. B equals 1 minus R. Alright? And then we just solve for R. And then from there, the rate of decay is 0.2 or 20%. This means that the value of the car decreases by 20% each year, which makes sense because that's what happens with the value of a car. All right, so in terms of this situation, I think I'm gonna skip this one for you. No, we could talk about it. For the function of 24 times 0.8 to the power x can be used to model the value of a car of x years after its purpose. Graph it, which it talks about the domain. It didn't talk about the y-intercept and what do the asymptote represent. So actually, I'm glad that we are talking about this problem. This is a good one. So we gotta know what all this domain range asymptote, what does that mean in application? So you're talking about a car, and we know the value of a car decrease, right? So we gotta look at those y-intercepts and all of that. So in addition to, you gotta find the value of x when y is 5. So when we do that, meaning that when we try to find y is 5, we get 7. So what this is telling you, because the y-intercept, well, let's talk about the y-intercept. The y-intercept is 24. And that just means that the car initially, when you first bought the car, was $24,000. So that's your y-intercept. That's how much you paid for it, $24,000. The y-intercept means that, the asymptote tell you that the value will approach zero after X amount of years. So it's not going to be $0, but that just means that it's just going to get closer and closer to zero. So, we start out 24,000, you could be worth hundreds of dollars out of that. All right. So when we talk about the domain, when we look at this, because the domain is all real numbers, but you got to think of it in this case. A reasonable domain would be 0 to 12, as most cars are sold within 12 years. So this piece right here revolves, having an understanding of cars, which even I don't at times. So I'm not really going to spend too much time on it. But the asymptote piece, that's something that we do need to know how to do. All right. So from here, when you plug in 5 for y, in terms of this model, when you plug this in decimals, you should get 7 for x. So that means that the value of the car will be about $5,000 after 7 years. So, simple as that. Shouldn't be too complicated. It's just, understand the real life situation of a car operation. And we can work more on it if you need help. So, what I want you to do, try that problem, follow the steps we just did, and see what you can come up with. If it says something about the domain, don't worry too much about the domain. I don't need for you to get your heads, thrown off about that. But this deals with population of hawks, so you don't need to worry about all that. All right. Ooh, it's number 5. Ooh, 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 ooh. We getting there, y'all. Oh, this is a long video, but we hang in there. All right. So, a museum purchased a painting and a sculpture in the same year. Their values are changing exponentially shown, which artwork is increasing more quickly. So, when it comes to art, I don't know about you guys. You go to someone's house. Well, speaking for myself, I like buying art. Now, some of my art pieces I do have, they are quite, they were a pretty penny I paid for, but over the years, they're going to be worth more money. So, you know, and the more famous the artist, the bigger the money. So, in this situation, you just gotta look at the graph and see which one's increasing more. So, then once you identify the key structures, because it's increasing, just you follow the model and look at your growth factor, and then plug in like you've been doing, and then using that formula. So it's going to tell you which one's worth more money. So, all right, I want you to try this problem out. You look at the previous information. And again, we could talk more about this in class. All right, so look, your key important features of this is dealing with exponential growth and exponential decay. I showed you what it means for something to grow and what it means for something to decay. So, again, things like cars, the price of a PlayStation 5, right now, it started off at 500 some dollars. But I know during COVID, the prices originally were skyrocketed to 700 originally, and then the prices started diving down. Now you can find PlayStation 5 at 450. So that's a decay model. So things like money, population, that's a growth model. All right, so these are just additional problems that you don't necessarily need to do because they are pretty much essentially the homework. All right, let's deal with 6.2. We almost done. And this deals with compound interest formula, continuous compound interest formula. The natural base E, that's not something that we're going to talk about. Well, we are, so we're going to deal with it. All right, identifying a rate. So this is similar to what we did in the other lesson, but there's a slight difference to it. But everything's still the same. Use decimals, good to go. Write a little answer, keep it moving. So in 2021, the population of a small town is 8,000. The population increased at a rate of 2.5% per year. We write exponential growth function to find the monthly growth rate. So when we say in the word monthly, how many times is that out of the year? So monthly is 12. All right. And it's monthly, so it's going to be 1/12 out of the year. So apply the formula like you've been doing before and keep it moving. when you do that, you should be good. Now, one thing I want you guys to understand is when they decided to plug this guy in right here. When you plug in this guy right here, this becomes that. But before we continue, let's go back to what Ms. Antoine taught us. 2.5%. We convert that as a decimal. It's going to be 0.025. Make sure you know how to do that. All right, so let me help you out just a little bit. Um, ooh. Okay, I'm gonna get back to that momentarily. For some reason, I missed that one, but I'm gonna explain it to you. Regina invests in the money of 12,600 in the account that's compounded continuously. What is the value of account after 12 years? So when it says the words continuously, you're using a different formula, which is PERT, P-E-R-T. So P is your starting amount, which is that 12,600. Your rate, well, your rate is going to be 12 years, right? You get 12. I mean, no, your time is 12. Your rate is 3.2%, which is 0.3, which is 0.032. So put this in decimals, you get this answer. And of course, rounding to the nearest dollars, you get this statement right here. All right. So you should be able to put this straight into decimals, and it should be good. All right. So in this example, you see, just apply the PERT formula, P E R T. All right, yeah. You guys are so awesome. So let's finish this up. In the previous examples, when they was talking about monthlies and stuff like that, this is what I was asking you guys for. Using this formula right here. All right. So when you get compound interest, and when it's talking about like monthly, because monthly is 12, and quarterly is 4. So just watch out for that particular language. So when you see language like that, monthly, quarterly, regardless of years, use this formula. Now, if it's in 6 years, 8 years, if not telling you quarterly, bi-weekly, weekly, all of that, then use this formula. Now, if it said compound continuously, I mean that will never ever stop continuously, use this formula. So those are the keywords that you need to use. All right, guys, you guys been so awesome. Thank you guys so much. This should help you with your homework. And if you need further assistance, refer to your notes. Anything that was missed, refer to the video.